Hello everyone, welcome to Sweetie Speaks official YouTube channel. This is Computer Architecture series. In the previous lecture, we had learned about Von Neumann Architecture and Harvard Architecture. In case you missed those video lectures, I request you to kindly go through them first so that you will understand this modified Harvard architecture in a better way. I will share the link for the Von Neumann architecture and Harvard architecture in the description. Let's get started. As the name suggests, modified Harvard architecture. It means the basis is Harvard architecture, but we have modified something. Let's see what we have done. Modified Harvard architecture means we are trying to loosen the strict separation between data and code. Code means instruction. If you remember, in Harvard architecture, we had separate data and instruction memory. In modified Harvard, we are trying to lose this separation a bit. We'll see how we are going to loosen it, what are the different ways we can loosen it, that we are going to see. But please remember, this is the main feature of modified Harvard architecture. The second feature is it still retains the high performance concurrent and concurrent access to data and instruction. As we had in Harvard, we were able to access data and instruction simultaneously. Similarly, we can do that in modified Harvard architecture also, but it provides some advantage because we are going to loosen the strict separation between data and instruction. There are three types in which you can loosen the separation. The first one is split cache, in which you are going to have the same main and secondary memory for instruction and data, but in the cache you are going to have separate data and instruction cache. The second one is access instruction memory as data. The name is self-explanatory. We are going to access instruction memory as if it was a data. The third way is read instructions from data memory. Earlier we were only having data in data memory, but now we can also read instructions as well from data memory. Now let's see all these three types in detail to understand how this modified Harvard architecture is providing us advantage over Harvard architecture. Let's understand the first type, which is split cache. As the name suggests, we are splitting the cache memory. You can say that split cache is a combination of Von Neumann and Harvard architecture. The main and secondary memory are same for instruction as well as data, which means the main and secondary memory follow Von Neumann architecture. But cache memory is separate for instruction and data, which means cache memory is following Harvard architecture. Separate caches for instruction and data. This is the split cache. Let's see the second type, which is access instruction memory as data. Before going into this, understand one thing. Instruction memory is usually in ROM, which is read-only memory. Read-only memory means you can't edit that memory. And data memory is read and write memory, means I can edit the data memory. This is one thing which you should remember. Now let's understand how accessing instruction memory as data helps us. It eliminates some of the limitations in pure Harvard architecture. What were those limitations? In pure Harvard architecture, we cannot have a pointer to code. First thing is instruction memory is read only memory. So say for example, at the current moment, I just wanted to assign code to a pointer which is a null pointer, and later on at the runtime I want to assign this pointer a value. This is not possible in case of Harvard architecture. You don't have that flexibility to have a pointer to the code which you can edit later. This is not possible in pure Harvard architecture. But in modified Harvard architecture, we can do this. In pure Harvard architecture, you cannot read code as data. Since you cannot treat code as data, if you remember, code memory is read only memory. It means the code is fixed. You can't edit the code at all. It is not possible to reprogram your instructions in case of Harvard architecture. But in case of modified Harvard architecture, you can read your code as data. So you can reprogram your code. You have these flexibilities in modified Harvard architecture in case of access instruction memory as data. In this modified Harvard architecture, we have some special set of instructions. What these instructions help us to do is they will help us to access the instruction memory as data, and they will allow reading constants from code memory into CPU registers. It is possible that there are some constants in your instruction memory. So these constants can be read into your CPU registers in this access instruction memory as data type, because if you put it in your registers, the access is more faster because registers are very close to your CPU. So this helps in accessing the constants very fast. How does read access happen? Initial data values are copied from your instruction memory into the data memory at the start of program. So there can be certain data values which are inside your instruction memory, initial values, which we need at the start of the program. These values can be copied into data memory. Then say if data is not going to be modified. If the data is not going to be modified, it can be accessed by running program directly from instruction memory, because the data is not going to be modified. So whatever data value is at the start of program in the instruction memory, it will remain same. So why should I use up data memory? No use to no need to waste the data memory. I am going to use directly instruction memory, the data values in the instruction memory, thereby saving the space in the data memory. Why? Because my data is going to remain constant, it's not going to be modified at all. How does write access happen? Write access means you are able to write to the instruction memory. It's not just read only memory. Since you are accessing instruction as data, you can reprogram it. This is helpful in some purposes like software updates. If you want to update your software, you want to reprogram it. This capability is available in access instruction memory as data. Now let's see the second type, which was read instructions from data memory, which means that you will have instructions in instruction memory, but you will also have instructions inside your data memory. It provides some improvement over pure Harvard architecture. Let's understand what are they. It allows executing code from the data address space, because now you are also having instructions inside your data memory. That's why you can execute this code or instruction from your data memory also. You can implement self modified code. Now whatever instructions are present in data memory is read or write memory. So whatever is present in this data memory, you can go and edit it. It means you can self modify the code. It is possible to modify the instructions which are present inside your data memory. You can execute the instructions fetched from any memory segment. You will have instructions in instruction as well as data memory. You can fetch the instructions from data memory also and execute it. As well as you can fetch instructions from instruction memory also and execute it. How is this advantageous? If you remember, we discussed about one limitation in Harvard architecture, that you have a fixed instruction memory and there is no flexibility that if you have a large code base, you can use the data memory as instruction memory. In such applications where you have large code base, you can use this architecture, read instructions from data memory, wherein you can also have certain instructions in your data memory, and thereby you can expand your instruction memory so that you can run a large code base also. How will you distinguish between Harvard, pure Harvard, and Von Neumann? There are few distinguishing features. Let's understand them one by one. First is address space. Now, if you remember, we said that in pure Harvard architecture, there is separate instruction and data memory. It means the instruction space will also start from zero address, and the data space will also start from zero address in case of pure Harvard architecture, right? Now, what happens in case of Von Neumann architecture? If you remember, in Von Neumann architecture, we said that there is going to be same memory for instruction and data. It means only one address space, instruction or data, will start from zero. Only one address space, because this address space is going to be shared. Now, if you talk about instruction memory as data modified Harvard architecture, this will also have a separate address space, because you are having instruction memory and data memory separate. Just you are at times you are able to use instruction memory as data. So both will have the address space which starts from zero. Now let's see the second distinguishing feature, which is hardware paths to the CPU. Now, if you remember, in case of Von Neumann architecture, we have same pathway to CPU for data as well as instruction. In case of pure Harvard architecture, we have separate hardware pathways to CPU. We had separate buses, right? In case of pure Harvard architecture. Now, in case of modified Harvard architecture, in which instruction and data memory share an address space, it can be treated as von Neumann until the cache coherency becomes an issue, as with self-modifying code and program loading. Don't confuse it. You can just remember that if it is a modified Harvard architecture and you are still having separate instruction and data memory. Say, if you remember, in case of split cache, we said that only cache is going to be split. It means only for cache you are going to have separate hardware paths. But in the case of split cache, if you remember, main and secondary memory were having same instruction and data address space, so they will also have the same paths to the CPU. This way you can remember what happens for the modified Harvard architecture. The third distinguishing feature is memory access. How are you going to access the memory? So if you remember, in case of this von Neumann architecture, we had the same memory for instruction and data. In case of Harvard architecture, we had different memory, and even the memory access was different through different buses. But in case of modified Harvard architecture, we had different ways, if you remember. In case of split, we just split the uh, instruction and data cache. It means the memory access to just the cache is different. But if you remember, we also had we had some other configurations in the modified Harvard architecture, which was instruction memory as data, in which you can also access instruction memory as if it was a data. And we also had something called as data memory as instruction, in which you can execute data memory as if it was an instruction. This is how the memory accesses were different. I hope with this you are now able to understand all different types of architecture based on the instruction and data memory. It was von Neumann, pure Harvard, and modified Harvard. To stay tuned to such video content, please subscribe to Sweetie Speaks official YouTube channel. Thank you.